In the last videos, we discussed basic notions of graph theory. It is now time to go back to the motion planning problem. In this video, we will see how we can formulate motion planning problems as a graph search problem. We can use graph search to solve motion planning problems in which the configuration space has low dimensionality. There are 3 steps in the process. Step 1 is creating a graph that encodes the planning problem. Step 2 is using a graph search algorithm to obtain an optimal path. Step 3 is translating the path on the graph to a trajectory in configuration space. For many problems, it is sufficient to use a generic graph search algorithm that is not specific to robotics. Most of the complexity is done in the first step. Let's see how we can encode a motion planning problem as a graph. The nodes will represent robot configurations. The configuration space is continuous. If we want to use a graph, we need to discretize it. There's a trade-off. The more nodes we use, the better the method's accuracy, but the computation time will increase. The edges between nodes represent possible motions that the robot can use to go from one configuration to another without touching obstacles. The edge labels represent costs. For example, we could take the cost to be the time it takes to go from one configuration to the next. Of course, we will not put in the graph nodes that correspond to configurations in which the vehicle collides with the obstacles. Once we have the graph, we can apply a generic shortest path algorithm. The graph search algorithm does not know anything about the motion planning problem. It just reasons in terms of nodes, edges, and edge costs. The solution will be a path in the graph. We'll then need to translate it back to a trajectory. The query for a shortest path problem is a directed graph, with edges labeled with non-negative weights, an initial node and a target node. The result is, if it exists, a path in the graph that starts at the initial node and ends at the target node. The path is optimal if its total weight, which is the sum of all the weights along the path, is minimal among all feasible paths. There are many graph search algorithms, varying complexity and performance on different types of graphs. We will see 2. The first is Dextra's algorithm, an example of an uninformed algorithm, and A*, an informed algorithm. Dextra's algorithm was invented by Dutch mathematician Oscar by Dextra. It belongs to the family of algorithms that explore the graph starting from the initial node until they find an optimal path. There is a queue that contains nodes to be explored. For each node, we keep track of the cost to come, the cost of going from the start to the node. We also keep track of the edge that we'll use to arrive there. Initially, the queue contains only the start node, with a cost to come equal to 0. At each iteration, we pop the queue element with the smallest cost to come. If it is the goal, we have found the optimal path. Otherwise, we look at the node successors and compute their cost to come to this node. If the successor has never been visited, we put it in the queue. If the successor has already been visited, we put it in the queue only if the new cost to come is lower than what was previously computed. When we pop the goal node from the queue, we can reconstruct the optimal path because for each node, we kept track of the edge that got us there. We are sure that we have found an optimal path because the algorithm always pops up nodes with the smallest cost to come. If at any point the queue is empty, then we can be sure that there is no solution. A* is an algorithm invented at Stanford that is able to perform an informed directed search. It uses a heuristic function, which is an optimistic estimate of the residual cost to go from a node to the target. In motion planning problems, we typically have good heuristics. For example, if we are planning the minimum distance path in a city, we know that the optimal distance cannot be lower than the direct distance from a node to the goal, straight as the crow flies. A* expands first nodes with a minimal estimate of the total cost, given by the sum of the cost to come and the estimated cost to go given by the heuristic function. This allows the search to be directed towards the most promising nodes, rather than expanding in all directions like in Dextra's algorithm. It is a simple argument to show that the first feasible path we find is an optimal solution if the heuristic function is optimistic. With a good heuristic function, A* greatly outperforms Dextra's algorithm. In fact, you could see Dextra's algorithm as a special case of A*, where the heuristic function is 0 and therefore not very informative. Dextra's and A* are examples of generic graph search algorithms that we can use for solving low-dimensional motion planning problems. There exist variations of A* tailored for robotic scenarios. For example, it is common in robotics that after a robot plans a path and starts executing it, it becomes aware that the path is not feasible anymore. due to new abstractions. The D-star family of algorithms invented at Carnegie Mellon can efficiently solve these replanning problems, in which the graph changed by reusing the information already computed that is still valid. In this video, we discussed how to translate a motion planning problem into a shortest path graph search problem. Using standard algorithms such as Dextra and S*, we can solve low-dimensional motion planning problems.